applications as the application of PEM bottle electrolyzers and associated bottlenecks. In the beginning, I will go through introduction about myself and about the department established at UQTR. Following by the PEM bottle electrolyzer, its cost breakdown, associated challenges, and finally, I will conclude my today's talk with the mitigation strategies, which are ongoing research in the field of PEM bottle electrolyzers. So hello everyone, I am Sukhvant Singh, second year PhD student at UQTR Canada, working on PEM bottle electrolyzer applications for green hydrogen production. I did my master's from NIT Trichy in chemistry in 2022. After that, I joined IISc Bangalore as a project intern for 6 months and then went to Hanyang University, South Korea as a research student. And now I am in UQTR Canada pursuing my PhD in the field of PEM bottle electrolyzers. Our department in UQTR University is IRH, Hydrogen Research Institute. It was established by an Indo-Canadian professor. He was Professor Tapan Kumar Bose in 1994. It is North America's first hydrogen research institute. Apart from hydrogen research facilities, we have here a couple of hydrogen-powered vehicles and hydrogen filling station, which is green hydrogen filling station, and green hydrogen which can be produced through the wind energy, which is also located at IRH department. As we can see that the global primary energy consumption has increased sharply since the mid 20th century, still dominated by fossil fuels such as coal, oil, and natural gas. However, we can look at electricity production. We can see that gradual rise in renewable energy sources, specifically wind and solar, although their share is still relatively small, very small compared to the conventional energy sources. But have a look on these data. These graphs show how global greenhouse emission and CO2 emissions have risen sharply over the time, specifically since 1950s. China and US and other South Asian countries are now largest emitters. The increase is closely linked to the industrialization and energy uses. These highlights the urgent need for global action to reduce the emissions. And if we see the data of air pollution, these graphs show that global death rate from air pollution have steadily declined. However, the burden remains high in regions like South Asia, specifically in India. While some regions shows strong progress, others still facing some serious health impacts from pollution. This highlights the need of continuous efforts to reduce air pollution worldwide. So what is the solution for this issue? Only one solution we have in our hands is use of renewable energy sources rather than conventional energy sources. Let's have a look on available renewable energy sources. This slide shows the main sources of renewable energy, including solar, hydro, wind, etc. These sources help us produce green and clean electricity without relying on fossil fuels. The energy generated can be stored in batteries and used in various sectors, for example, electric vehicles, houses, industries, and transportation system. This transmission is key to reduce the emission and building a sustainable future. But no doubt, these are the only energy ecosystem we have widely accepted, and it is also still not raised to its full potential, specifically in our country, India. But this ecosystem comes with some limitations because we have to store the energy in the same device which we are using for energy conversion, as well as the limits, as well as the energy storage. So what other options we have to overcome the limitations? We don't have a lot of options. Here, hydrogen energy can help us to overcome the limitations by providing the separate conversion and storage ecosystem. Now, this is how we can actually create a renewable energy and hydrogen energy ecosystem to overcome the limitations of battery devices. We have a couple of types hydrogen available, like based on the origin from where we are generating that. But green hydrogen is one of the best option to reduce the greenhouse emissions. We can use renewable energy to produce the green energy or green hydrogen and store it After that, we can reuse that hydrogen with the help of fuel cells to further get the electricity and the water as a byproduct to power our industries, transportation, and personal uses. Just imagine we are producing green hydrogen in the summer from solar energy and utilizing that electricity in the winter, and also getting water as a byproduct. We have couple of types electrolyzers which are almost commercialized and near to commercialize, like alkaline water electrolyzer, anion exchange water electrolyzer, and solid oxide electrolyzers. Among them, PEM water electrolyzer is one of the best electrolyzer, which comes with advantages like large operational range, fast dynamic response, high operating pressure, and highly pure produced gas, hydrogen gas. It took birth in early 1962 via Gemini Apollo space program, and then first commercialized stack developed by General Electric, and then first 100 kilowatt electrolyzer stack was built by ADT with the collaboration of BBC. And today we are here. In PEM water electrolyzer, we can apply the current to split the water into the oxygen and hydrogen atoms at the anode side of the cell by the help of iridium or ruthenium catalyst. Protons then travels to the cathode side through the proton exchange membrane, and then to the help of platinum catalyst produce hydrogen gas without any other major byproduct. Let's have a look how a single unit of PEM bottle electrolyzers looks like and how it works. In this single cell of PEM bottle electrolyzer, in the heart of the cell, there is a proton exchange membrane coated with iridium and the platinum from anode and cathode sides respectively, and sandwiched between the metallic PTL and carbon-based GDLs from anode and cathode side both respectively. And then this sandwich further compressed between two bipolar plates with gaskets to supply the water and remove produced gases. And this complete assembly fixed with the help of end plates. A PEM bottle electrolyzer stack can have more than one single cell at the scale-up level. These components are really essential components and cannot be replaced or altered. Some of them are highly costly and highly durable. On the other hand, some of them are highly sensitive and prone to degradation easily. A PEM bottle electrolyzer can be run up to 80,000 hours at favorable operating conditions in its lifespan. It just needs proper supplies of water and electricity. Now, if we see the individual cost of these components, 55% of cost goes to the balance of plant, which includes hydrogen processing, system cooling, power supply, and water circulation. And almost 55%, 45% of the cost comes under the operational expenditure, which is the stack cost. And if we further break down the stack cost, a major cost goes to the metallic component, surprisingly not with the precious catalysts uh, compared to other electrolyzers. Catalyst takes almost 25% of cost, and in the next slide we will see how 70% of the cost goes to the only two metallic components, which are uh, bi bipolar plates and the PTLs. Uh, Almost 70% of cost goes to titanium based two components. On the titanium, one is the bipolar plates and second one is the titanium based post transport layers. And why these components are so costly? Because if we see the operating conditions at anode side of the PEM bottle electrolyzer cell, it has high anodic potential, a low pH, acidic nature of proton exchange membrane, and heat flux at reaction sites. This environment is perfectly harsh to corrode the metallic based components during the long-term operations. That's why we have to use a titanium based bipolar plates and PTLs, because titanium is highly stable metal under acidic operating conditions. But titanium also comes with some serious limitations. Under acidic operating conditions, titanium forms oxide layer on the surface very easily, and that oxide layer protect metal from further corrosion, but also hinders the cell performance. How? Because this titanium oxide layer is less conductive, increase the contact resistance, and reflects higher operating voltage, eventually increase the operating expenditure of the cell. Means after the titanium oxide formation, now we have to burn more power to produce same amount of hydrogen gas. And you can see this is how titanium bipolar plates and the PTLs looks like after the corrosion during the long-term operations. Actually, this is the main issue of the electrolyzer, specifically PEM bottle electrolyzer, make it highly costly technology to adopt commercially. Apart from resistance increase, corrosion of titanium can also trigger the metal ions dissolutions, also called catalyst membrane poisoning. Structural degradation of titanium PTL results in porosity changes that will further reduce the mass transportation, including efficiency losses like, as we discussed, increased over potential and reduced overall durability of the PEM bottle electrolyzer cell. So as we discussed, the main issue with the titanium-based bipolar plates and the PTLs, there is one main commercialized mitigation strategy, which is worldwide used with the industry, which is coating of precious metals on the surface of titanium components. Why precious metals coating is the way? Because noble metals are highly stable under acidic and high potential conditions, prevents direct exposure of titanium to the electrolyte, surpassing titanium oxide growth. These metals have high thermal conductivity and provides excellent electrical conductivity. Finally, results in a reduced ICR, which is interfacial contact resistance, and also maintains the better performance at high current densities during long-term operations. And these coatings make these components economically sensitive, highly costly. You can make a guess how costly these are actually. Commercially available bipolar plates and titanium PTLs, they actually comes with more than 200 nanometer thick and noble metal coating. That is the main bottleneck of PEM bottle electrolyzer technology, apart from the catalyst and the membrane part. Now, how we can further reduce the precious metals utilizations? Over the time, researchers have explored various methods like non-precious metal coatings, for example, niobium, tantalum, and their carbides, nitrides, and hydrides. These metals has potential. They have really good potential to replace the precious metals containing coatings, but comprehensive research is still remains, because a single cell of electrolyzer can run up to 80,000 hours. So we have data, benchmark data with platinum, iridium, and gold and ruthenium, but we don't have that much of research data with the help of with using niobium, tantalum carbide, and hydrides. So still, it required a comprehensive research, systematic research. And if we use these metals as interlayer, bimetallic, or alloy form with mixing with the precious metals like platinum and gold, they can improve the corrosion resistance further and eventually reduce the precious metal usage. Different coating methods also can help to reach the target, like sputtering method can precisely control the loading and desired morphology. That will also help to reduce the precious metal utilization, because electroplating method, which is worldwide used and accepted by the industry for the coating of bipolar plates and the post transport layer PTLs, it's very notorious
Yeah, Mr.
method.
Sekwant, 4 more minutes, please.
uh, no problem. So electroplating method is worldwide accepted method to coat the bipolar plates and the titanium post transport layers. And electroplating is very notorious method. It's very hard to control the loading of the precious metals. So what sputtering can offer, that can, it's very easy to control the loading during the coating of metallic components. Even we can reach 1 nanometer, 2 nanometer, 3 nanometer with the help of DC magnetron sputtering or RF magnetron sputtering. Or we should have some other options than titanium metal, like uh, stainless steel, carbon based, and the conductive polymer based, or niobium and tantalum based bipolar plates to substitute the bulk material, which is titanium. But we should know and we should keep in mind always, uh, substitution of bulk material always comes with new challenges. And also we can utilize 3D printing to overcome these issues, to improve the grain boundaries of the metallic components, And because 3D printing provide us better machining options of the components, means better machining means better grain boundaries, and better grain boundaries means better corrosion resistance. And eventually we have to use less precious metals for the coating to protect those components from corrosion. These all are the ongoing research in PEM bottle electrolyzer community, specifically associated with bipolar plates and the PTL's developments. These days, SS-based components are extensively explored by the researchers, and they are giving good results to move forward further for long-term durabilities in industrial level. But as I mentioned previously, substitution of bulk material also trigger the new challenges. So extensive systematic research is still challenges in the field of bipolar plates and the titanium PTLs, specifically associated with PAM bottle electrolyzers. So here I conclude my today's talk. So finally, I really want to acknowledge to CECA Vadodara, Ahmedabad University, Green Hydrogen Conclave organizing team members, including Dr. R.K. Singh. And finally, I would like to acknowledge my university, UQTR Canada, to providing me the resources. Thank you, guys.
Thank you so much.
Thank you.
Thank you for giving an insight on proton exchange membrane, which was again an offshoot of the space technology. The earlier Apollo and now the current electrolysis is used in the International Space Station for recycling the water. And you also touched upon the various technologies which are being attempted to reduce the cost of the electrolysis. Thank you so much. So, if I can have one question, if anybody has, for Mr. Sukhvant.
Yes, please.
If there are no questions, I would like to thank Mr. Sukhvant for